gene actually codes for which protein. So that was something that they wanted to find out. So they wanted to go back and see, they wanted to, in other words, to fish out genes and see what genes code for which proteins. And one of the way that you can actually know that a gene in fact exists for a protein, the only way to know that is this, is by seeing if there are any mutations, are there any mutations that actually hinder the growth of an organism, and if there are mutations, then what genes that is. The only way to find that out is actually by irradiating, by exposing a certain plant or certain species to radiation. Here what they did was they took Neurospora, which is actually a fungus. They took the fungi and they irradiated it. Normally they know that Neurospora can actually grow on minimal media. I think minimal media is the one in which you need some basic nutrients. You don't need all the nutrients. So Neurospora can't synthesize its own nutrients. It just needs some minimal media. So once you irradiate them, you don't know which of them have undergone mutations. Some of them might have undergone mutations and some genes are kind of destroyed, but probably some Neurospora actually were exposed to radiation, nothing really happened to them. So just to be sure, after they irradiated, what they did was they started growing the irradiated Neurospora on complete media. If you grow them on complete media, either they have undergone mutations or not, they will definitely grow. Once you have that irradiated culture growing on the complete media, they picked up each spore and then they transferred it to minimal media from there. Now, if you move those from complete media to minimal media, in case they have undergone mutations, what happens is they will stop growing. Now they went back to the cultures where they were growing it on complete media, and they added it to tubes with one with one amino acid extra, so to speak, to see if a gene for the synthesis of a given amino acid is mutated or not. So to show it to you in the image, so if you look at it, this is Neurospora that's been exposed to it's been irradiated. Now they might have undergone mutation, you don't know, so you transfer these Neurospora to complete media. Now they definitely grow on complete media, irrespective of the mutation. After growing on complete media, they now move each spore to minimal media. Now here you can see that one of the Neurospora here is not growing. Now they know that, now they go back to the tube with complete media and say that, okay, this Neurospora has undergone mutation, and now they move this Neurospora from the complete media to minimal media once again, but the only difference is that they add one extra amino acid as a component. When the Neurospora starts growing on one of the tubes, now they know that, okay, all right, so probably in this case, for example, at least, arginine has actually been, the gene for the synthesis of the amino acid arginine has been mutated, and that's why this Neurospora is not growing on minimal media, and now once you add arginine, it's growing back. So this was one way for them to find out, actually, to know if a given Neurospora or if a given species has a certain gene for the synthesis of a certain amino acid or not. Then they asked the question, if you add arginine to the irradiated Neurospora and if it's growing on it, then the question is the gene for arginine, is the enzyme for arginine synthesized mutated, or is the gene that comes a little early in the synthesis of arginine that's mutated? So is the mutation here, or is the mutation here or here? In this case, let's say arginine has 2 or 3 precursors like citrulline, ornithine, and some other precursor. What they did was they started adding, so they took this mutated Neurospora and they started adding it to tubes that only had citrulline or only had ornithine or only had a much earlier precursor, and they started to see when do they start growing and when do they actually stop growing. Thereby, they were able to kind of map a pathway for arginine synthesis. So as shown in this image here, you see this is wild type. Wild type Neurospora can grow on just minimal media. I mean, it can grow on minimal media with other precursors for arginine. So they grow on all of them. You see the brown ones? But here, for example, this is group 1 mutations can grow on minimal media supplemented with ornithine. They cannot grow on the precursor that comes before ornithine. So here you see group 1 is blocked at this stage. For example, if you add the precursor to the Neurospora, and if they don't grow, it's a clear indication that the enzyme required for the synthesis of ornithine is blocked. So eventually you will not have ornithine is blocked, so eventually you will not have arginine synthesized. Or in the other case, for example, if you add the precursor and ornithine is being synthesized, then this pathway from here for the precursor to ornithine is fine. In the second group, when you add citrulline, and for example, if you add ornithine, and if you don't see citrulline, then you know that the enzyme B, for example, for group 2 here, this one is blocked here. So which means the enzyme required for ornithine to citrulline is actually mutated in the irradiated Neurospora, leading to no synthesis of arginine. Likewise, in group 3, if you add citrulline and if you don't see arginine, then obviously the next step, basically the enzyme required for the conversion of citrulline to arginine is actually destroyed. So this way, they started not only finding out which of the genes have been mutated, and they said, okay, all right, so you have a gene that's required for the synthesis of arginine. And then they said, wait, let's go to the precursors, and eventually they mapped out all the pathways required, all the enzymes required for the synthesis of arginine. And it has to be kept in mind that this kind of pathway mapping or gene mapping for the synthesis of arginine, for example, works only if these precursors, only if the precursors here are actually enzymes, because enzymes have the ability to convert a substrate into a product. Okay, they have the ability to convert a substrate into a product. So if this precursor, which is actually synthesized by a gene, for example, if this enzyme, which is a product of a gene, if this is not an enzyme, if it's just a protein, then obviously this method will not help you to map the pathway for arginine synthesis. Is that clear, guys? Any doubts on this? So then they said, then they kind of postulated the concept called one gene, one enzyme hypothesis. But in this situation, you have to assume that every gene codes for an enzyme. Every gene codes for a protein, but it's not guaranteed that every enzyme is, it's not guaranteed that every protein is an enzyme. So then they said that sometimes for enzymes to be active or for proteins to be active, you have many polypeptide chains. So one polypeptide chain combines with the other polypeptide chain to form a complete enzyme or a complete protein. So then they said probably one gene does not code for an entire protein in every case, but it definitely should code for at least one polypeptide chain of a protein. And so they modified the hypothesis and they said it one gene, one polypeptide hypothesis. Is that clear, guys? So this is actually, in simple words, they kind of started doing some experiments where they could start saying that, okay, if it's growing on arginine, and if it's not growing in the absence of arginine, then they said probably there is a gene that is required for the synthesis of arginine. So that's how they map the genes. Now, going forward, then they started looking at, what is the structure of a protein? What actually makes up a protein? And for protein structure, when you look at the basic unit of a protein, it's actually amino acids. They're called amino acids because they have an amine group and they also have a carboxyl group, which is actually represented here as an acid. So this is amine and this is an acid, or basically a carboxyl group. That's why proteins are known to have acidic and also a basic group. When a peptide bond needs to form, the carboxylic group of one amino acid reacts with the amine group of the second amino acid. In this process, a water molecule is removed, eventually forming a peptide bond. So peptide bond is formed between two amino acids by the removal of a water molecule. So if you are supposed to break a peptide bond, so you need an enzyme to break the peptide bond, and you also need one water molecule to break this peptide bond and generate two amino acids. Okay, either way. But Here we look at the synthesis of a peptide bond. Now, looking at the structure of a protein, proteins have multiple structures. Basically, the primary structure of a protein is directly referring to the amino acid. So if you look at a string of amino acids stretched across, and when you find, let's say, a stretch of amino acids, that is actually referring to the primary structure. So the primary structure is nothing but a string of amino acids linked to one another. And when these string of amino acids actually fold, they form something called the secondary structure. There are two commonly known secondary structures. One is the alpha helix and the beta plated sheets. Here they said beta plated. Either way, it's beta plated sheets and the alpha helix. The secondary structure, which is nothing but the alpha helix and the beta plated sheets, they can actually fold further due to more interactions between those amino acids to give something called the tertiary structure. Now, you have to remember that here, from here to here, I can still call it one polypeptide because this is the primary structure, it folds, it further folds to form tertiary structure. So one protein can have a tertiary structure, or in other words, one polypeptide can have a tertiary structure. These polypeptides, which have a tertiary structure, each polypeptide can combine with another unit of itself to eventually form a quaternary structure, because sometimes more than one polypeptide combines with one another to form a quaternary structure, which is actually a very complex structure. And one good example for that is hemoglobin. One of those protein examples for quaternary structure is hemoglobin. Hemoglobin is a good example of a quaternary structure because it has two alpha chains and two beta chains, two beta globulins and two alpha globulins, something like that, which gives you a quaternary structure. So this is the primary structure of a protein, which is nothing but a sequence of amino acids. This is the secondary structure where they begin to fold. So you have the alpha helix and the beta plated sheets here, and this is the tertiary structure, which further folds. And so this could be one polypeptide chain that's folded in this way. And now when you have multiple polypeptide chains combined to form one protein, so basically multiple tertiary structures combined to form one protein is called a quaternary structure. It's important to remember that not all proteins have a quaternary structure. Some proteins could have a quaternary structure, some could not have, some probably do not have a quaternary structure. Moving on to the genetic code. So the set of nucleotides that actually encode a single amino acid is actually referred to as a codon. We now know that you need every codon has three nucleotides. That's what we know now. But initially when they started off, they did not know if the codon had two nucleotides or three or four. So imagining that the genetic code is only made up of one nucleotide, so A, G, C, and U. So the possibility is you would have a possibility of only coding 4 amino acids, but we know there are a total of 20 amino acids. So they imagine that probably the genetic code is actually, the genetic code has 2 nucleotides. In this case, you only have 16 possible combinations. Then they said probably the genetic code is a triplet code. Then you have about 64 possible combinations, which is actually more number of codons, more possible combinations for just 20 amino acids. And they said probably it's a triplet code. So the initial experiments to test it out to really see if its genetic code is just 2 codons or 3 codons. One of the early scientists who actually worked on the genetic code, but actually Marshall Nirenberg and Henry Schmidheim, Johann Henry Schmidheim, they use an enzyme called polynucleotide phosphorylase. The ability of this enzyme is that no matter which nucleotides you give it to the enzyme, it kind of links them up and forms a very long thread. In this case, what they did was they just gave it uracil. Let's say they gave a few thousand uracil nucleotides, and they added the enzyme polynucleotide phosphorylase. The enzyme will add up all these nucleotides one next to one another and create a chain of uracil nucleotides, which probably stretches like, I don't know, a few hundred or few thousand nucleotides. Then they took about 20 test tubes and they added radio labeled amino acids in these test tubes. But the only difference is that every test tube only had one amino acid which was radial labeled. So let's say you take one test tube with arginine, all the arginines in that is actually radial labeled. Likewise, they took 20 test tubes with only one amino acid, but this amino acid was radial labeled. And when they added this this uracil molecules which were linked to one another, what they found was they found protein synthesis only in the tube that had phenylalanine. Because let's look at this here. They took uracil nucleotides. Now you create something called a uracil homopolymer, which is nothing but a string of uracils linked by this enzyme called polynucleotide phosphorylase. Now what you do is you incubate this homopolymer of uracil with with enzymes and amino acids. Then what happens is you spin it and you kind of get rid of the single amino acids and filter out the protein. Now you just see which of this protein is actually radial labeled. By doing that, they found that in that test tube where only which had only phenylalanine, they had a protein synthesis. Basically, protein synthesis was only found in this tube, which indicated that uracil UUU coded for phenylalanine. So doing this, you can actually find out for UUU or GGG or AAA or CCC. But then after this, they extended the study. Okay, this is methionine, but I think we spoke about them last lecture. So doing that, you can only find out 4 amino acids using triplet codes. But then this was the experiment they started off using. Sorry, I'm jumping back and forth. They used homopolymers, which is not either UGC or A. But then later they started using heteropolymers. So they kind of substituted not just uracils, but they added extra nucleotide like adenine to uracil, and then they started looking at the possible different combinations, and eventually they kind of found out as to which which codon codes for which amino acid. So they kind of mapped out all the 20 amino acids and which codons actually code for the 20 amino acid. So here they eventually end up having 64 possible codons, hoping with the possibility where it is a triplet code, and they found out that 3 codons mentioned here like UAA, UAG and UGA, they do not code for any amino acid at all. So thereby, they said that these 3 codons don't code for amino acids, so they call them the stop codons, whereas the remaining 61 codons were actually referred to as the sense codons. You call them sense codons because they code for one amino acid. Since you have only 20 different amino acids and you have 61 codons, obviously more than one codon is coding for the same amino acid, and that's exactly why they said the genetic code is degenerate. And also, codons that specify the same amino acid are said to be synonymous codons, because more than one codon is actually coding for the same amino acid. So these codons together are synonymous codons, and the genetic code itself is actually termed degenerate. So look at this. So since here you have like 4 codons, sorry, you have 2 codons coding for phenylalanine, 2 for leucine, and 4 more for leucine. So these 4 plus these 2 here, all these 6 are referred to as synonymous codons. Synonymous codons. These 4 and this 2, because all 6 of them code for leucine. But in general, the whole genetic code is actually degenerate because more than one codon codes for the same amino acid. And then moving on, like if the cell has to synthesize proteins, then amino acids have to be supplied to the ribosomes. And transfer RNAs serve as adapter molecules for this. Now, what do transfer RNAs do? Transfer RNAs are very specific for the amino acid that they carry. Every transfer RNA can only carry one specific amino acid. So each type of transfer RNA attaches to a single type of amino acid. Some amino acids are carried by more than one transfer RNA. So basically, what it means is, if you have a genetic code like that, and let's say if you have a codon which is CUU, then, like I said in the previous lecture, you need to have a transfer RNA which has anticodon. This is a codon, and at the base of every transfer RNA, you have something called an anticodon. So, looking at that, since you have so many codons, and so the cell should also have transfer RNAs which should have that many anticodons. So transfer RNAs that accept the same amino acid but have different anticodons are called iso-accepting transfer RNAs. So this is your messenger RNA with the codon here, and this is your anticodon. And for example, UCC actually codes for serine, because this transfer RNA has serine linked to its 3' end. And also it's important to remember that sometimes the third nucleotide here need not really match exactly, but still the transfer RNA will sit on the messenger RNA which has serine linked to it. If you look at it here, you have AGG, which the anticodon is AGG and the codon is UCC. Here you have UCU, and here, but instead of having an A here, you have a G here. So even though sometimes the third codon is not exactly a match, still the transfer RNA will sit and actually will supply the serine amino acid, which can be linked to the growing polypeptide chain for protein synthesis. Guys, is that clear? I mean, I'm going a little fast because I've already done this in the previous lecture. I don't want to be too slow. All right. Now, the reading frame and initiation codons. In general, the genetic code is non-overlapping because, for example, if you take humans, at least the first three nucleotides, which is referred to as one codon, will code for one amino acid. The next three will code for another amino acid. Thereby, you have only one reading frame. But as I mentioned earlier, that viruses usually have the ability where they can shift the frame and try to synthesize at least 3 different proteins from the same codon. This is a evolutionarily conserved method used by virus so that even though they have a very small genome, which is only a few million nucleotides in length, they can synthesize all the different proteins that they want by shifting the frame. So in humans, if the first 3 nucleotides code for one amino acid, the second 3 for amino acid, in virus, for example, it can skip the adenine in the beginning and start reading from UAC, and that UAC can synthesize for tyrosine. Likewise, it can skip A and U and start from ACG, and that can actually code for 309. Using this is also referred to as frame shift, but there's a probability of 3 different frame shifts or 3 different reading frames. In humans, you only have one, but some viruses try to use 3 different frames and try to synthesize 3 different proteins. So the first codon, even though a ribosome sits on the messenger RNA at the 5' end, it does not synthesize the amino acids. Only when it sees the first codon, which is usually AUG, which is codes for methionine, it starts synthesizing the polypeptide chain. Or in other words, once the ribosome starts sliding over, it encounters a transfer RNA sitting on AUG, holding methionine at one of its 3' end. That's exactly when protein synthesis actually happens. Protein synthesis begins as the ribosome slides over the messenger RNA. The initiation codon is usually always AUG, which is methionine. Although in some situations you might have valine or also leucine, can be used in rare occasions. So these are the termination codons which actually signal the end of translation, and that's because these these codons, they do not code for any amino acid at all. So there are no transfer RNAs that have anticodons to pair with the termination codons, and that's how protein synthesis actually terminates. Basically, there's nothing like terminating, but then there's nothing to add to, so to speak. That's exactly how protein termination happens. This is the table column giving you some rare exceptions, altered codons. So usually if the codon is AUG, it usually codes for stop codon, but in some bacteria, for example, like Mycoplasma, it could code for tryptophan. Likewise, in humans, AUG codes for stop codon, but the mitochondrial DNA can sometimes code for tryptophan. So these are some exceptions. You don't have to worry about memorizing all the information on this table column, but this is just to give you an overview as to what actually the codons code for and what could be some of the exceptions in some different species. Yes?
Do we need to memorize the amino acid table, the whole thing?
The genetic code,
Well, yeah, I guess that's what it
you speaking about this one?
is. Yep,
No,
okay, thank you.
no, I don't want that. I mean, I just want you to know them. At the best, I want you to memorize the stop codons and the start codon. Is that clear? I mean, I don't think that's really needed to. I mean, no. Right? Even this table of column is for you to have a look and get an overview, but no memorization. All right. So amino acids are assembled into proteins. So we know that ribosomes are protein synthesizing machines because that's where protein synthesis happens. A ribosome usually attaches at the 5' end of an mRNA, but even though it attaches at the 5' end, it kind of slides through that. It doesn't really start adding amino acids until it sees the start codon, which is AUG. So there are 4 stages for protein synthesis as a ribosome actually begins to slide over the messenger RNA. First is called tRNA charging. tRNA charging is nothing but you can have a tRNA and you can have a tRNA which is linked to an amino acid. When a tRNA is actually linked to an amino acid, it is referred to as a charged tRNA. So charging requires energy in the form of adenosine triphosphate. Okay? Then you have the next step after tRNA charging is initiation. So basically the beginning, in which all the components required for protein synthesis are assembled. Basically, the enzymes, the ribozymes, all of them are actually in place to start protein synthesis. Third is actually the elongation phase, where amino acids are actually linked to one another on the ribosome. So transfer RNAs move the amino acids. They kind of lodge it onto the ribosome, and the ribosome does the job of elongating it. Basically, it joins one amino acid to other with the help of a peptide bond. And eventually, there is termination where the ribosome reaches the stop codons, and by the time it reaches the stop codon, it sees that there is no transfer RNA with anticodons that can kind of match or kind of complementarily base pair with the codons. And that's where termination actually happens. So this is an image showing you an overview, the messenger RNA, and this is your start codon. Once it encounters the start codon, protein synthesis happens so that the ribosome actually slides over the messenger RNA, and here you can see each violet circle here represents an amino acid. Now, how is actually tRNA charged? Basically, how is an amino acid linked to a transfer RNA? So the enzyme that brings about, the enzyme that kind of links an amino acid to a transfer RNA is actually amino-acyl tRNA synthetase. So amino-acyl tRNA synthetases are the enzymes that actually link an amino acid to a transfer RNA. So if you're looking at this, the transfer RNA, it has a clover leaf shape. Now this is the region where you have the anticodons, which actually complementary base pair with the codons on the messenger RNA. Now at the very tip, you have 3 nucleotides, which is CCA. Usually for any transfer RNA, at the very tip, you will always have these 3 nucleotides, which is CCA. The only difference as to how do you know that that the transfer RNA is carrying is, how do you know that the transfer RNA is specific for an amino acid? That you're going to find out by looking only at the anticodons. But at the 3' end, you have CCA here, cytosine 1 is adenine here, and the amino acid is actually linked to the adenine molecule. So adenine is here, and you have the sugar, which is a pentose sugar. One end of the pentose sugar is actually linked to the amino acid. So that's how amino acid, that's how a transfer RNA is actually charged. So look at this. This is an amino acid with a carboxyl group. By using ATPs as an energy, ATP is broken down, and using the energy, adenosine monophosphate is actually linked to a amino acid. So this is AMP linked amino acid. Now in the next step, what happens is that adenosine monophosphate is actually removed, and this carboxyl groups links to the 3' end of an RNA to the adenine molecule. So every time a transfer RNA has CCA at the end, but transfer RNAs are specific for a given amino acid, and that is only known when you look at the anticodons. But at the 3' end, it's always CCA. So amino acid is always linked to an adenine nucleotide, as shown here. So now this is the 3' tip of the transfer RNA that's linked to a carboxyl group, and thereby it actually links itself to the amino acid entirely. Now that is the structure of a transfer RNA. It has 4 different arms, and if you look at here the 3' end, the blue regions are same in all transfer RNA. So this is what, this should be C, and this should be C, and this should be an A. These 3 shown in blue are CCA for any transfer RNA. And here this is the anticodons. So the anticodons is what defines which amino acid should be linked or should be charged to a transfer RNA. The position in red are important to the recognition of transfer RNAs by 1 synthetase. Okay? This is the extra arm, so you don't have to worry about, well, this is just giving you an overview of the structure of the transfer RNA. In general, it has a clover leaf model. It has four different arms. One is the anticodon on extra arm, and T, IS, yeah, you don't have to worry about all that, but all right. Now, looking about initiation of translation in bacteria. Bacterial protein synthesis is similar to eukaryotes with a small, with very few differences. For most of the process, it's almost the same. If you look at it, the initiation complex in bacteria consists of a small ribosomal subunit. So on the messenger RNA, the small ribosomal subunit is the first one that actually binds to the messenger RNA, because this small ribosome unit, like say ribosomes are actually proteins. Even though they are proteins, they have a small piece of RNA linked to the protein, and this small piece of RNA is usually complementary to the Shine-Dalgarno sequence. We know that the Shine-Dalgarno sequence is actually a consensus sequence found in the messenger RNA, and complementary nucleotides to this Shine-Dalgarno sequence are actually found in the small subunit of the ribosome. So ribosome is a protein, it also has a piece of RNA, and this piece of RNA is complementary to the Shine-Dalgarno sequence. Now, the second component that you need to initiate translation is the messenger RNA, obviously. Then, to begin protein synthesis, what you need is a charge transfer RNA which has methionine linked to it. It is referred to as FMET, tRNA IFMET. I don't know why they call it, why they refer to it as FMET here. Anyway, but that's how it's kind of represented. So this is the first transfer RNA which has methionine linked to it. You also need some other proteins for initiation. Here they are referred to as initiation factor 2, also called IF2. Then you need GTP because energy is broken, because when guanidine triphosphate is broken, energy is released. That energy is actually used to move the ribosomes or to link one amino acid to the other amino acid on the growing polypeptide chain. And all these together combined are referred to as 30S initiation complex, because you have a small ribosomal subunit, which is a 30S unit. Then you have the mRNA, the transfer RNA, the initiation factors, GDP. All these combined are referred to as the 30S initiation complex. Now, when the bigger subunit of the ribosome links to this 30S subunit initiation complex, now it is referred to as the 70S initiation complex. Okay? 70S initiation complex. Look at this here. So this is a small piece of RNA that is linked to the 30S subunit, which is a small subunit. And as you can see here, this is a Shine-Dalgarno sequence, and the nucleotide sequence on this small RNA piece of the small unit of the ribosome is actually complementary to the Shine-Dalgarno sequence. That's exactly how the 30S subunit actually attaches itself to the messenger RNA. As you can see here, this is the small ribosomal subunit which actually attaches itself to the messenger RNA, and this is the Shine-Dalgarno sequence here with some initiation factors. Now, the first transfer RNA, which has methionine linked to it, and the anticodons are actually shown here, it comes and sits on the messenger RNA. Now you have a messenger RNA, a transfer RNA with methionine linked to it, and the small ribosomal subunit which is bound to the messenger RNA at the Shine-Dalgarno sequence. After this, this is now referred to as the 30S initiation complex. The whole thing here, the transfer RNA, messenger RNA, small ribosomal subunit, and some initiation factors together, along with GDP, which is required for supplying energy. Now, the 70S ribosomal unit binds to the 30S ribosomal subunit, to the 30S initiation complex, forming the 70S initiation complex. Now, this is a step, this is the first step where protein synthesis can actually happen. So you need all these components sitting in that spot so that the ribosome now can slide over the messenger RNA. And as it keeps moving forward, new transfer RNAs, which are linked with amino acids, they start sitting on the messenger RNA, thereby supplying the ribosome with different amino acids. So those steps here mentioned here are actually that's what you see in eukaryotes, like let's say, sorry, in prokaryotes like bacteria. For eukaryotes, it's like the steps are almost similar. You have to remember that the 5' end of eukaryotic messenger RNA usually has a 5' cap, which is actually important for stability of the messenger RNA. The eukaryotes also need the ribosomes. Also, they need the initiation factors which are referred to as IF2 or IF3. The initiation codon linked to the transfer RNA, which is FMET transfer RNA, and the first nucleotide, which is the first codon, which is AUG, which codes for methionine, can act as a consensus sequence. So few nucleotides before the start codon and one more nucleotide after the start codon, all this entire unit acts as a consensus sequence. Even though this AG codes for methionine, you have to remember the whole thing actually acts as a consensus sequence, and this consensus sequence in eukaryotes is referred to as Kozak sequences. So the Kozak sequence includes the first codon with a few nucleotides surrounding it. Okay? This Kozak sequence is also recognized by the ribosome. Now, here you see the start codon at the 5' untransferred region, the start codon here and the stop codon with the poly A. So once the ribosome, or basically the 70S ribosomal complex sits on the messenger RNA, there are some cap binding proteins, some other proteins which actually stabilize the ribosome, and then the poly A tail, which we said is important for the movement of the messenger RNA from the nucleus into the cytoplasm, it actually bends over and kind of binds to these proteins, thereby stabilizing the complex. And also, sometimes they say the longer the polyethane, the faster the translation can also be, so to speak. So it also improves the stability. It also can speed up the translation process. Now, once this complex sits on the messenger RNA, it's now ready to synthesize the proteins, and this is the step referred to as elongation. Elongation is where amino acids are linked to one another by the creation of a polypeptide chain. So once you look at the ribosome, the 30S and the 70S ribosome, they actually have 3 sites within the ribosome. One is called the amino acid site, the second one is called the peptide site, and the third one is called the exit site. Amino acid site, peptide site, and the exit site. The initiation transfer RNA immediately occupies the P site, the only site to which the RNA carrying methionine can sit. So the first site to be occupied in ribosome is actually the P site. Okay. I want to jump to the image, but okay. So the first step, a charged transfer RNA will sit on the A site. Remember that the P site is actually occupied by the methionine, the transfer RNA carrying methionine. Then the A site is actually occupied by another transfer RNA which has anticodons to complement it to the nucleotides on the messenger RNA. And this requires some other elongation factors, or basically some other proteins which are required for the charged tRNA to sit on the A site. Now, a peptide bond is formed between the amino acids that are attached to the transfer RNAs in the P and A site. So in the P site you have one transfer RNA, in the A site you also have another transfer RNA. Now both of them actually are carrying one amino acid each, and the bond between these two amino acids linked to the transfer RNA is actually created by the ribosome. The third step is movement of the ribosome down the messenger RNA in the 5' to 3' direction, and this requires other proteins called the elongation factor G. So let's look at this in the form of an image. So this is the peptidyl site, amino acid site, and this is the exit site, EPE. First, the peptidyl site is actually occupied by the transfer RNA that carries methionine. This is the first one to occupy. Later, another transfer RNA occupies the amino acid site. Now, as the ribosome keeps sliding forward, the other nucleotides here on the messenger RNA are occupied by the transfer RNAs, which are the anticodons complementary to the messenger RNA. Now you can see here that you have 2 transfer RNAs sitting in the P site and the A site, and elongation factor TU is used here, and using GTP, what happens is it's broken to release energy, and that actually creates a bond between here the methionine and the proline here. So now you have 2 amino acids. So the first transfer RNA, which has methionine, is removed, but before it leaves, this methionine is actually transferred to the anterior tip of the proline here. Likewise, as more and more transfer RNAs begin to occupy the A site here, the peptide chain begins to elongate, and this requires elongation factor G. Is that clear, guys? Guys, you have any questions on this? Now, termination. Protein synthesis ends when ribosome translocates a termination codon, because by the time the ribosome reaches the termination codon, there are actually no transfer RNAs which carries amino acids. So kind of it encounters the termination codons, and there's no transfer RNA sitting there. So there's no way that a ribosome can actually generate a peptide bond. So at this spot, the proteins called release factors play a very important role here. What they do is They bind to the A site of the ribosome, and they promote the cleavage of the transfer RNA in the P site from the polypeptide chain. So thereby they release the polypeptide chain here. As shown here, you have a transfer RNA now which is linked to the last amino acid, but once it reaches the ribosome, encounters the stop codons, release factors sit on the stop codon in such a way that they kind of enable the release of the polypeptide chain from the transfer RNA. So this protein is now free and kind of float away, so to speak. All right. All this protein synthesis mechanism actually happens in the cytoplasm of the cell. Now, after it's done, the transfer RNAs, the release factors are actually, they detach from the messenger RNA. The ribosomes also detach, and if this messenger RNA has been translated into protein, basically if enough number of protein copies are generated, this messenger RNA is also subjected to a programmed degradation where this messenger RNA is broken into single nucleotides. And these nucleotides can again be used by the cell for the synthesis of another messenger RNA as per the requirements of the cell. Okay, this slide actually gives you the entire overview starting to the very end of it. So here you see the messenger RNA, the small subunit binds, the large subunit binds. You have the transfer RNA sitting here, and the ribosome is sliding over. Protein synthesis happening. Basically, amino acids are linked to each other with the peptide bond. Encounters the stop codon, the release factor sits here, and then the polypeptide chain is actually released from the transfer RNA. Is that clear, guys? So it's also important to remember that when protein synthesis happens, it's not just that one copy of the protein is actually synthesized. Multiple ribosomes sit on the messenger RNA, one next to each other. Thereby simultaneously you have hundreds, if not thousands, of copies of a given protein that is synthesized. For example, we know that cell requires practically millions and millions of copies of histone proteins because the DNA binds around histone proteins, right? So if histone proteins are required in such huge amount, obviously the messenger RNA for histones is heavily occupied by ribosomes, which help in the synthesis of thousands, if not millions, of copies of histone proteins. So the concept of polyribosomes can be very well applied for the synthesis of histone proteins. Okay, so this is an image showing you the messenger RNA in green and multiple ribosome units bound to the messenger RNA. See, look at it. As these ribosomes keep sliding over, you see new ribosomes are actually binding to the 5' end of the messenger RNA, and they kind of keep sliding over, and then multiple copies of proteins are synthesized. If you look at this here, every nodule represented here actually represents one ribosome, and if you follow this ribosomes, you could assume that this is probably also the messenger RNA. You don't see the messenger RNA here, you only see the ribosomes represented as some nodules. Is that clear, guys? There are some additional properties of RNA and ribosome after protein synthesis. So messenger RNA surveillance, one of the things is sometimes there could be some errors on the messenger RNA translation. So basically, as protein synthesis happens, accidentally sometimes the wrong amino acid could be added, or sometimes suddenly the protein termination can be initiated. When that happens, this messenger RNA is immediately subject, this protein is immediately subject to degradation, because the protein is not completely synthesized, and then this truncated protein could interfere with cell functioning. So there are cell machinery, some other proteins which destroy this polypeptide chain because protein synthesis has not completely happened. So eukaryotes have evolved a mechanism called nonsense-mediated mRNA decay, which results in rapid elimination of the messenger RNA containing premature termination codons. All right. So either way, protein degradation, or basically mRNA degradation, happens if the cell realizes that the messenger RNA, the message in the messenger RNA is not correct or not complete. Is that clear, guys? Any questions on this chapter? Did I go too fast? I have a feeling so. All right, let's take a 5-7 minute break, a 10 minute break, and then we'll finish. We'll go to chapter 16.